All right, let's talk about using translation using a coordinate grid and a coordinate system and how this relates to, say, college algebra and trigonometry where you're graphing functions and relations. So first of all, let's talk about this a bit. We actually looked at this a little bit in our last video when we're looking at GeoGebra. At some point, I turned on a grid and we saw how you could use the grid to help us. So you should probably already be able to do this from the last video. But first of all, let's remind ourselves that lattice points on a grid are points that are at the corners of the grid. Particularly if it's a Cartesian coordinate point, then they're the ones with integer coordinates. Uh, okay, so if the spacing here is 1 apart, any of the points there where these grid lines meet are called lattice points. And so a lattice polygon, such as these two triangles or this pentagon here, have that they're lattice points, lattice quadrilaterals or lattice pentagons, lattice polygons. So if you notice this vector right here is 1, 2, 3, 4, 5 to the right and down 2. Well, if you start with this pre-image of triangle ABC, we just take every point and just count over 1, 2, 3, 4, 5 to the right, down 2 to get 8A prime, 5 to the right and down 2 to get B to B prime, and same for C to C prime. Take your straight edge out, boom, you're done. So take this vector U and translate this purple pentagon by this vector u. So see if you can do that on your own as an exercise. Okay. So let me move on. Okay. So after you've done that one, let's move on here. So the next thing I want to look at is translations um, of relations in Cartesian coordinates. Let's go a step further. Not only do we have a grid, we actually have x and y axes on that grid, and then we have actual numbers related to the points now. So now we have coordinates, okay? Of course, this makes it into analytic geometry where we're connecting the algebra or the formulas and the arithmetic of what's going on there with the numbers, tables of numbers, with the geometry, the graphs, the pictures, the geometric figures. This relationship's analytic geometry. So let's look what happens when we change certain things in the formula. How does that relate to what's happening with the graph or the geometry that's going on? Okay, how do changes in the algebra affect changes in uh, the geometry? So let's start by taking a set of points, a geometric figure, that solves this equation y equals x squared. Now I just picked certain points on there. Now, of course, the domain of this is all real numbers for x and then all non-negative real numbers for y. But I've just picked some usual suspects here, -4, -3, -2, -1, 0, 1, 2, 3, 4. Nice little organized table that I just picked. And then I just picked the x values. And then, of course, I have to square them to find the corresponding y values. Square -4 to 16 to get 16, square -3 to get 9, and so forth. And we get these y values here. So I could take any representative thing. Now here's what I want to show you. If we will take this equation, take where the x is, and replace that whole thing by parentheses x x minus 5, okay, then what is actually happening in the table? Well, the formula, when you're thinking of it this way, is always going to be backwards. Okay, so when it says replace x minus 5, you have to compensate for that by basically adding 5 to x. So that's what we're going to do. We're going to leave the y's alone here because notice the y up here was left alone. But it was the x that was changed. But when it says x replace x by x minus 5, what you really do is add 5 to x. -4 plus 5 is 1, -3 plus 5 is 2, -2 plus 5 is 3, and so forth. And if you look, all of these do work. Why? Well, when you take the 3 minus the 5, you're back to the -2. You square it, you get 4. So you're going to end up at the same y over here. Notice that I'm not just making any table here that fits this equation. I'm making one so that I'm thinking of that right there as a pre-image image pair. I'm thinking of -416 being mapped to 116, and negative 2, 4 being mapped to 3, 4. Well, what does that do on the graph? Well, here's the blue graph is the pre-image. That's these points and all the other ones that would make this work. It actually goes on forever. It's a shape we call a parabola. There's a geometric definition for a parabola that we're not going to be able to get into right now, but there's a parabola, that shape. You should be familiar with this one already. And so what we're going to do is we're going to actually just add 5 to all these things. So every one of these is shifted exactly to the right 5 units. So it's a horizontal translation. So if you look here, there's a pre-image point here, straight to the right 5 is its image point. So the graph is just shifted or translated to the right 5 units. Okay, so what if we replace, let's take another example, y equals x cubed. Again, let's just take the same x's. This time when we cube them, we get these numbers here. That's this graph here. Power function, y equals x cubed. And this time, again, we're leaving y alone, but we're replacing x by x plus 6. So again, when I make my table to make them correspond, I need to make sure that when they're lined up like this, they have the same y coordinate. So all I'm doing is just copying this part of the table and pasting it over here. And I have to figure out what to do for the new x's. Well, if you replace x by x plus 6, what you're really doing is subtracting 6 from the x. So negative 4 minus 6 is negative 10, negative 3 minus 6 is negative 9, and you fill out the table that way. But then, of course, you can always check it by plugging these numbers back in here. For example, negative 6 plus 6 is 0, cubed is 0. Let's just do it over the negative 3 plus 6 is 3, 3 cubed is 27, and so forth. So it does work. So what do we really do? We really subtracted 6 from the x's, so we shifted to the left 6. See how it just shifts to the left. We can do the same thing with the y's to get vertical shifts, vertical translations. Okay, and this one here, well, again, we'll start with the same two base graphs, y equals x squared and y equals x cubed. But this time we're going to replace y by y minus 3. So I think it's easiest to see it if you look at it in this form right here. Because in this form you can see that the x side was left alone. What was changed is y was replaced by y minus 3. Now you could solve this for y, particularly like if you're going to put it on a, say, a TI-84 calculator or something like that, you need to solve for y. So you could say y equals x squared plus 3, but it's not as obvious which one is changed here. Rewriting it in this form right here makes it clear that x was left alone and y is changed. So if I want to match up pre-image to image here, I need to copy my x column over so that when I line them up like this, they have the same x. X did not change, y changed. How did y change? Well, here y was replaced by y minus 3. What do you really do? You subtract 3 from y. So 16 minus 3 is 19. 9 minus, you add 3. It's y minus 3 here. In reality, you add 3. So 16 plus 3 is 19. 9 plus 3 is 12. 4 plus 3 is 7. And so forth. Well, what does that do? That's going to shift it up 3 units. So here the pre-image is here, and the image is straight up above. So it's the same size and shape. It's a congruent figure. It's just shifted up 3 units. It's been translated. Okay. Over here we start again with y equals x cubed. That's the one going through the origin there. And again, we just cube each one to get the corresponding y's here. But when we match it up, we're replacing y by y plus 2. Okay, you can solve for y if you want, but this is probably the better way to think of it for what we're doing right at the moment. And so you replace y by y plus 2. What's really happening is you're subtracting 2 from the y's. So negative 64 minus 2 is negative 66. Negative 27 minus 2 is negative 29, and so forth. And so what we see is, again, we're lining up not just any two tables, but we're lining them up so that we have pre-image and image lined up. That was what's indicated by all these little arrows here. Right? And so what's happening, the x coordinates are staying the same, so it's just moving straight up and down. In this case, it's moving straight down 2 units. Okay? Now, we can just put these two ideas together and translate by vector. So if we want to translate, say, by the vector negative 4, 3, we can think of that as two transformations, one by going to the right 4 and the second one by going down 3. Of course, it's really just one transformation, but one translation by that vector. But as far as the algebra goes, to get the 4 part, you're going to the right 4. You just replace x by x minus 4. And to get the down 3 part, you just replace y by y plus 3. Now, in this particular case, since we're doing just translations, the order doesn't matter. You can go, you can do the left to right first and then the up or down, or you can do the up down and then left to right. However, I'm going to give you a quick warning. When we compose other types of transformations, the order does matter. So let's be a little careful with that a little bit later on. But right now, it doesn't really matter. So for example, we want to take, again, let's take a usual suspect, y equals x squared. And we want to translate it by the vector 4, negative 3. So we're shifting right 4 and down 3. So replace x by x minus 4 and y by y plus 3. Remember, the formula is backwards. So just take the y, put y plus 3. Take the x, put x minus 4. If you want to solve for y, you can. But it's probably easiest to see it in this form right here that's what's going to happen. So what's going to happen here is I just picked some points here. I went from negative 2 to 2 with the integer values, squared them to get these. And to get an idea of what we're going to end up with, what I should end up doing with, so I'm translating by this vector 4, negative 3. It's not backwards. You're actually adding 4 to x and adding negative 3 to y. So negative 2 plus 4 is 2. Negative 1 plus 4 is 3. 0 plus 4 is 4. 1 plus 4 is 5. 2 plus 4 is 6. And then we're adding negative 3 to the y's. 4 minus 3 is 1. 1 plus a negative 3 is negative 2. 0 minus 3 is negative 3, and so forth. And so if we put these dots here and these dots and graph them and connect the dots where we're supposed to, this one should give us the graph, portions of the graph y equals x squared. That, in this case, is the green one right here. And notice you can see some of these points, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. And then we see the corresponding points down here. So the one that correspond, let's check it out, negative 2, 4 was right here. And if we from there, we go right 4 down 3. So that was here. We go 1, 2, 3, 4, and down 1, 2, 3. We end up at this point right here. What is that? 2, 1. Yeah, that's what we came up with, right? And so you just do that for all the points, and you can see them. Draw any one of the vectors from one of these points to the pre-image point to the image point. You got a copy of that vector for negative 3. So that's how you can do general translations with a coordinate system. It works out. So here's an exercise for you to do. Translate the function, the y equals x cubed, along the vector or by the vector negative 6, 4. First of all, what's the formula of the new relation? Set the new table for this, not just any table for the new relation, but one that matches up pre-image to image, thinking of as a translation, okay? And then graph both the original graph, and the graph of the image, pre-image and image. Pre-image is y equals x cubed. You come up with the formula for the image. And you should be able to do that by hand. You should also be able to do that in something like, say, GeoGebra. Okay, let's keep going just a little bit. Another way that we can give functions is in parametric form. So let me just talk about this first. So here's a parametric form of an equation. X equals 3 cosine of t, y equals 5 sine of t, and t goes from 0 to 2 pi. In this version of a function, the input is t and the output's an ordered pair xy, and these formulas tell you how to get both x and y. You can think of this, a lot of times we can think of this very much as t being time, for example, and xy locating a point in the plane. Okay, that ordered pair is a point in the plane. So what's going to happen here is as time goes on, in this case from time 0 to time 2 pi, this that t is going to increase from 0 to 2 pi, but what does the point x and y do? Well, it's moving around the plane. So it's tracing out some path. And so that's basically the idea of a parametric equation. This one is actually an ellipse. Here it is right here, the blue one. If you start with, say, 0, we'll just work out a couple of these things. Cosine 0 is 1, times 3 is 3, sine of 0 is 0, times 5 is 0. So that starts at 3, 0. That's right here. And this particular one, as t gets a little bit bigger from 0, the cosine is going to get a little bit smaller, the sine is going to get a little bit bigger, and so the thing is going to go this way. So it's going to start here at t equals 0. It's going to go around this way. T actually turns out to be the angle theta, right? So it turns out to go from 0 here, t goes to pi over 2 here, t goes to pi here, 3 pi over 2, and at t equals 2 pi, we're back where we started. So it turns out to be a simple closed figure there. It's actually an ellipse. All right, so there's your pre-image, okay? Now, what's the image going to look like? Well, when you're translating by a vector, say this case, the vector 3, -4, we want to take that graph, go to the right 3 and down 4, which you can see it here. You know, every single point, like this highest point, you go to the right 1, 2, 3 and down 1, 2, 3, 4. This particular point right here, right 3, down 4. Here's one here, right 3, down 4. Okay? Every point is right 3, down 4 from pre-image to image. These three are 3 different copies of that same vector 3, -4. All right, so well, how do you do the equations of that? Well, it's super simple, and it's not backwards on this one, okay? All you have to do is the new x has to be 3 bigger than the old x, so you just add 3 to the formula. And the new y has to be 4 less than the original y, so you just subtract 4 from the formula. So it's real easy to come up with the new formula in parametric equations, as long as this vector is in component form anyway, is you just add those components to the x and y components to the x and y formulas. Formulas are not backwards from the translation where they were before in just regular xy graphing. All right, so here is an example for you to look at. Translate the graph of the relation y equals 2 cosine of t and x equals 3t. There's a parametric equations for a graph of some kind, whatever that is. Okay, and take that and where t is going to run from 0 to pi, and translate that by the vector 2, -2, 5. So write down the parametric equations for the new relation. Draw the graphs in GeoGebra for both of them. Okay, so maybe let me show you a couple of these things in GeoGebra while we're at it. So here's GeoGebra. Let's actually turn on the axes so we can see. Okay, and I've got a grid where it's spaced out by 1. That's nice. So if I start with the formula, you know, anything we want. Let's take an ellipse, for example. Well, yeah, let's take an ellipse. That's fine. X squared. Well, let's just take an upper part of ellipse. Y equals the square root of 25 minus 4x squared. All right, so we got a nice little upper part of an ellipse, upper half of a semi-ellipse, okay? So that's our pre-image, okay? What if we want to translate that? What if we do that? What if we take that same formula, see if I can get up here and copy it, copy, paste it here, but change x to x minus 3. Look what it did. It actually shifted to the right 3. And if I took this right here and replaced this by saying y plus 5, it'll actually shift that one down 5. So now this original image has been shifted to the right. Kind of went off the screen there for me. Let me see if I can refresh this in any way. I don't want to stay on the page. Let's see here. Well, let's change it a little bit. Let's see if this will do it. I'm not sure why it's not getting the full shape. It should be that full shape just translated. I'm not sure why it's not. It's changing as I move things around a little bit, which is zooming in and out. This is not too good. It should be doing exactly the same thing. Okay. So what did we translate by? We translated to the right 2 and down 5. So it's translating by vector AB. I think we have that vector. I thought I had that vector up here. Maybe I didn't have it anymore. Yeah, here, vectors. Yeah, vector AB is vector V. Okay, let's see if I can get it this way. What if I translate this by, okay, okay. I want to translate, where's my original function? F. So let's see if we can go to the input right here and just say translate, see if it'll take this, F by vector V. Yeah, that gives us the full thing. That's what it's supposed to look like. And it should, let me just type it in again. Y plus 5 equals the square root of 25 minus 4 times x minus 2 square. Huh. It's not liking the graph. I don't get it. It should look just like that one. It should look like that translated image. It should look like that. Okay, but you get the idea at least of what's happening there on the of trying the formulas. Now you can do parametric graphing on GeoGebra as well, and the command there is curve. Okay, so you do in curve, and you give it the x and y coordinates. So like if we say y equals x, or just say x squared, the x will be t square, and then the y is cosine of t, and then our variable is t, that's our parameter, and we want t to run from say 0 to 10. Okay, and we get, let me zoom out a little bit. We get that curve there. You can see part of it at least. Okay, let me try something else. Let me change it a little bit. Let's see, where is that? Parametric curve right here. Let's let x be curve sine of t, and y be 3 tangent of t, and let t run from 0 to pi. Okay, so we have that. Let's just get rid of that. Okay. Probably actually has an asymptote there. Yeah. Let's go, actually tangent's undefined at pi over 2. So let's just go to pi over, perhaps we just go to pi over 2. Okay. All right, so we have that little portion of a curve, whatever that is. And let's actually make it go. Let's go a little bit shorter. Let's just go to power of 4. So now we just have this little piece right there. Okay. Now let's take, that's D. Okay. So now I should be able to translate D by, say, the vector V, which is there. Okay, there it is. So everything should go to the right and then down 5. Okay. Can we write the formula for that? Yeah, we should be able to do that pretty easily. So here's our curve. So our new curve, this should graph on top of that one. It should be just take the original thing, sine of t, and then add the x coordinate, which is 2, how much x is moving to the right, and then do tangent of t, 3 tangent of t would be the original, and then take to that and just add to the y coordinate, which is, or the y change. And again, we just want to run t, same thing, power 4. And that should give us the new thing. So where are we? If I turn off the translate, see that one's still there. That's this one. We turn it off and turn on the translate one, they get that, turn that one off, turn that one on. Same thing. Okay, so that shows you a little bit how you can do parametric graphing in GeoGebra. Shows you how you can transform it from the algebra part or just by using the transformation commands, and you get the same thing. All right, let's stop right there for this one.